This is question number 7 from section 2.3. The problem is asking in part A to show that a constant multiple of a solution of equation, which I'm denoting with this star, so I'll refer to this differential equation as star. It's the equation of a damped harmonic oscillator, but I'm going to refer to it as star. And the question is saying, show that if you have one solution, then any constant multiple of it is also a solution. So in part A, we're going to look at, in part A we look at that. So I'm going to say let y sub p of t be a solution of equation known as star. I want to show, and I'm going to let y sub q of t be a constant multiple of y sub p. So c is an element of the real numbers. So any real number. So to check that it's a solution, I plug it in. So I'm going to check. And I look at what is, I have, m, erase that, m times the second derivative of y sub q dt plus b times the first derivative of y sub q plus k times y sub q. And I want to see if that adds up to be 0. Well, I can substitute for sure that in place of y sub q, I can put in the constant times y sub p, and in place of y sub q here, I have the derivative of a constant times y sub p, and here k times the constant y sub p. And I'm testing to see if that equals 0. Well, properties of derivatives, the derivative is, has the property that the derivative of a constant times a function is the same as the derivative of the constant, is the same as the constant times the derivative of the function. The same is true for second derivatives as well. The process could be done twice, or the same is true. And so I can write this as mc times the derivative, the second derivative of y sub p of t. I don't need to write the t, I apologize for that. Second derivative of y sub p with respect to t. And here I've got my k, c, y sub p. I'm still testing if that's equal to 0. Well, there's a common term of c here, here, and here, and I'm going to factor that out. I'm going to take my equation up here to the top, and I'm going to factor out my c, and I see that I have just an m times the second derivative of y sub p plus b times the first derivative of y sub p plus k times y sub p. And I know from the fact that y sub p is a solution means that if I were to plug in y sub p here, these terms would add up to be 0. And so I know, using y sub p, that this expression must be a 0. And so therefore, c times 0 is 0, and I have shown that yes, y sub q, which is some constant multiple of y sub p, is also a solution. On the next slide, I'll look at part B of this problem. In part B of this question, the problem is saying, look at a specific example. So here is a second-order differential equation that describes the damped harmonic oscillator with a mass maybe of 1, since the coefficient there is 1, perhaps. But in general, this is a type of equation we're trying to solve, and because of the nature of it, we're going to assume that a solution would be of the form y of t equals e to the st. And if you take the second derivative of it and add it to 3 times the first derivative of that function plus 2 times the function and factor out e to the st, we're left with an s squared plus a 3s plus a 2. The only way that that product is going to be 0 is if this term is equal to 0, and it can be factored, and we see that s is equal to minus 2 or s is equal to minus 1, and two known solutions, therefore, will be y of t is equal to e to the minus 2t, and y of t is equal to e to the minus t. And this problem is asking us to show that a constant multiple of one of these solutions is also a solution. So show that, for example, a function, I'll call it y, just y. Show that the function y of t, which is a constant multiple, let's just pick 5, for example, as a constant, of e to the minus 2t. Show that that is, in fact, also a solution, is also solution. So I plug it in. I take the second derivative of 5e to the minus 2t. I add 3 times the derivative of 5e to the minus 2t. And 2 times 5e to the minus 2t. And I want to see, does that equal 0? Well, just as in the previous example, the derivative of a constant times a function, the constant can be brought to the outside, here and here. And so I will rewrite this as 5 times the second derivative of e to the minus 2t plus 3 times 5 the derivative of e to the minus 2t plus a 2 times 5 e to the minus 2t. And I'm testing to see if that's a 0. Well, there's a common term of 5 here, here, and here, so I'll factor that out, and I'll write it as 5 second derivative of e to the minus 2t dt, 3 e to the minus 2t dt plus 2e to the minus 2t. Now I'll do the differentiation, which I'll do quickly. The second derivative will leave us with a positive 4 e to the minus 2t. The first derivative will leave us with a minus 2, so 3 times 2 e to the minus 2t. And still we have a 2 here, e to the minus 2t. erase that little glitch, and we're drawing parentheses and we're asking if that is 0. Well, I'm going to factor out the e to the minus 2t, and I have a 4 minus 6 plus 2 e to the minus 2t. Is that a 0? And sure enough, this term is 0, and so yes, we have found that a constant multiple, the 5 was chosen at random, times one solution is again a solution. So on to the next page. In part C, we are asked how many solutions to the equation do you get if you use this observation along with the guess and check method? Well, we know from part B that we have a way of finding solutions. This is a solution, and this is a solution. I'll call it y1, y2, e to the minus t is a solution. And so now that we know that any constant multiple is also a solution, we have an infinite number of solutions. Have an infinite number of solutions of the form y of t is equal to a constant times e to the minus 2t, or y of t is a constant times e to the minus t. And we're going to see more in the next chapter of how we take advantage of this fact. Thank you.